Hi, everybody. Can you hear me okay? This is Nalini Elkins with Industry Network Technology Council. Maybe you can send me a quick note to tell me that you can hear. Okay, thanks so much, guys. Okay, let's go ahead and get started. So this is a part of a series of multi-year, webinar efforts to help move enterprises towards IPv6 deployment and adoption, and to find a number of problems that affect people, actually more than enterprises, that affect everybody really, which we'll talk about today. We thank you so much to ISIF Asia, who has given us a grant for the India Internet Engineering Society, partnering with INTC, and we are lucky to have some of their board members on this call as well. And so if they want to say a few words, please feel free. It's a great collaboration with India. If you are in the APAC region and want some deployment assistance, then please do apply for this grant with ISIF Asia. There's a fair amount of money that is available. So please go ahead and go to their website. So let's go ahead and get started. I think quite a few of you know me already, but I've spent a fair amount of time in the industry, worked at the IET, participated at the IETF a fair amount, and continue to do so. So what we're going to talk about today is IPv6 extension headers and some of the issues and testing that we have been doing. This is a very hot topic at the IETF for the reasons that you'll see when I start explaining to you some of the testing that we have seen. And we have Mike Ackerman and Dr. Mohit Tahiliani on as well, and they are panelists, so they should feel free to throw their 2 cents worth in as appropriate, because they have been involved in helping to test. So let's go ahead and get started with what is the issue here. So if you look at the IPv4 header and the IPv6 header, you'll see that the IPv6 header is actually quite a bit simpler than the IPv4 header. It's a great deal larger, but that is only because the source and destination address are quite a bit bigger. What has happened really is that a number of the fields which were felt to be not always used were moved to extension headers, and we'll talk a little bit about that. So in IPv6, there is this concept of the next header. If you're used to IPv4, that would generally be your upper layer header, your TCP, UDP, quick, that kind of header. But in IPv6, it can be another header. If you've looked at IPsec, oftentimes in IPv4, IPsec was backported to IPv4, and you'll see the AH and ESP header, and they will be chained as they are in IPv6. That's essentially the concept. So what we have is this IPv6 main header. It is fixed. And the next headers are in what is called a TLV format, which is a type length value. And this is why we need these extension headers, is because if you went ahead and put that same thing in the IPv4 header, you could have a very large header indeed. 44 bytes. And so the idea was to try and compress it as much as possible. So this is what we mean, is you have chained headers, and there's a lot of rules for these. They can appear only once, except for destination options. Destination options can appear multiple times, and they must appear in a fixed order. So, for example, extension header 1 will say the next extension header, next header is 5. Extension header 5 will say next one's 8, and so on until you get to the data packet. And the last extension header is actually your upper layer protocol. This is what we're used to thinking of as the upper layer header in IPv4. So for example, you might have this. You might have in the IPv6 main header, it says the next one is 0, which is hop by hop. Then it says the next one in there is fragment header number 44. And then it says the next one is the TCP payload. So you just follow the chain, and there you are. So these are the common ones. Let's talk a tiny bit about each one, and then we'll do a deep dive into these. Hop by hop, that it's what you think is that every hop, every node from the source to the destination, every router in between, every IP addressable node. Now, you know, there might be some that are not firewalls, for example, that are in between, middle boxes we call them. Those are not considered a part of the hop by hop. So any IP addressable node will look at this, and that's why it's the first one. Is that since everybody has to look at it, you want it to be first. And then there is the routing header. This is a huge area where things are changing. And it's worth a discussion all in itself. So we'll leave that for the moment. If there is interest, we will talk about this whole area. One of the big things that was done is fragmentation was moved out. The reason being is that in IPv4, you can fragment anywhere along the path. Any router or whatever, if it gets to there, it can fragment the packet. In IPv4, there is only source fragmentation. What that means is that only the initial site, the initial node that is sending, can do fragmentation. Of course, that then it's like, well, how do I know what's on the path? And then so you have to do path MTU. So that leads down a very interesting other path that we won't go into right now, is that in itself is an interesting area. But this whole thing about when the fragment header was moved out, there were some interesting other things that happened. And this whole thing is actually the reason that maybe what I think 12, 15 years ago that Michael and I first got involved at the IETF. More about that momentarily. So the other things I think you may be familiar with, ESP and AH, those particular ones have been back-ported to IPv4, and most people are fairly familiar with those. Destination options is a new one to IPv6, and this is the area that we have been working on. And it's a very interesting area, and there is a great deal of activity in people defining destination options. So let's take a look at a packet trace. So here we are here. This is our good old, let me see if I can get my little highlighter, make it a little easier. Okay, So here's our IP header. All right, so you can see IPv6, correct, nothing in the flow label, interesting. You can see the next header here is the hop by hop option, header type 0. And then in the hop by hop header, it says, well, the next header is an ICMP v6 header. And then here comes the ICMP packet. And so that is how it works. It is fairly straightforward. One of the interesting things you'll see is that these headers are defined in what they call TLV, type length value format. For example, you have next header, which is the type, which is the hop by hop option, the length, and then the value itself. Now, the problem is, anytime you see that there's a length, what do you know? You know that it can be a variable length, because if it was a fixed length, you would not need to put a length code in. If you have variable length extension headers or variable length anything, what happens at that point is that it becomes difficult to parse, both in the code and in particular in hardware. Hardware likes to have short fixed length packets, and then so you can flip through. And if you even think about writing code, you can see how that would be, you can very easily do that as well. In code, is that you just flip through and you say, I know this header is always 10 bytes, let me flip through. So that has been one of the long-standing controversies over extension headers, is that people who manufacture hardware say, well, we don't want to spare cycles to process it. There's also a discussion about, if you use extension headers, will it go through a slow path, where that means that it has to be processed in software rather than hardware. These are very, very interesting questions. Having said that, I do know that there are people who are trying to, at least having the discussion about processing extension headers in hardware. We ourselves are looking at this in research mode. Let me just put it that way, purely in research mode, to see if because there is programmable hardware now. But anyway, so the controversy and the push-pull in this whole arena is extending function versus speed, because you can use extension headers to do a great many very, very useful things. But if you're going to sacrifice performance, why then possibly you don't want to do that. So again, that is the controversy. And this is what I was talking about, type length value. This has to be read. And the hop by hop header has to be read by every device. And again, this in particular has caused some heartburn. That is the technical term between people, because as you can imagine, if this were inappropriately used, you can see that you could trivially create an attack on various portions of the internet. Indeed, right? Having said that, it can be very useful for things. Imagine to yourself, if we could do a true trace route where every hop actually was able to tell you how much it spent in terms of processing. That would be very, very helpful. So it would not be a guess It would be a true measurement. That would be quite useful. But having said that, it has to be balanced with the potential harm that might be done by this. So as I say, this is all the controversies and the work in progress. So let us talk now about the fragment header. Fragmentation, of course, is done if you have one interface which wants to send, say you have a jumbo interface that wishes to send a huge packet, but the other devices cannot read such a big packet. Well, it has to be fragmented so that they can read it. And then you put in a fragmentation header and say there is more to come, and then you end up with a reassembled. So you can see here, this particular one is going out at what, 1440, and it says the next one is the fragment header. You will notice that in the fragment header, there is a very interesting field called identification. In IPv4, that was known as the IP ID field. And even though it was never intended to be that way, in practice, what many people did who were diagnosticians is used this IP ID field as a de facto IP sequence number. For example, because in IPv4 it is in every field, it is in every packet, and it need not be sequential, but in many cases it was indeed sequential. And so your first IP packet, whether it was TCP, UDP, or whatever, would be 1. The next packet from that IP stack would be 2, and so forth. So it was a very, very useful diagnostic tool for doing after the fact diagnostics, because there is no sequence number in IP, and that is how it was used, even though never intended to be that way. So this is the fragment header, and if we think about the cases for what should be blocked and what should get through, then you might just think to yourself, it would be very awkward and difficult if the IP fragment header, extension header, was blocked, right? You would be blocking an essential function of IPv6. How would you ever know that something was getting through? That's, so that is, even though you can have certain attacks which misuse the fragment header, on balance, blocking fragment headers completely would likely lead to a number of problems in transmission. So another very interesting option, extension header, is the destination option extension header. And the reason this is interesting is that it is set at the source and destination, and there is an open question as to whether things in the middle, the routers in the middle or any other devices, can or should be able to read it. The reason I find this so interesting is that this is, to me, one of the real strengths of IPv6. This kind of thing where you can have an extensible protocol, by which I mean that when new needs are discovered, you can define a new destination option. One cannot foresee years into the future what might be needed, what kind of new devices will be invented, what kind of new protocols will be invented. But if you have a way to extend the protocol, then the protocol is likely to live and survive. If you think of it in a particular way, this is the way to create mutations. If you use the evolution analogy, you can mutate and you can evolve by creating new options as they are needed. And so to me, this is one of the reasons I have spent a great deal of time and effort in this whole arena, is I think this is it's a crucial area for the survival of this particular protocol, which, like it or not, is not going anywhere. There is no IPv8, IPv10, much to some people's chagrin. So, this is a sample of an IPv6 destination option. This is a mobile IPv6 one. Interestingly, yeah, not to digress, but it would be mobile IPv6 has not necessarily seen the adoption one might wish, but you can see here that within the main header it says IPv6 destination option coming next, and it will tell you which type of option it is, and then you have the next header, which is the mobile IPv6. If necessary, there will be padding that is done for word alignment. I believe it's only, I don't believe it's double word alignment, but single word alignment. And you can see that is how it works. So there are interesting things that can happen with IP headers. So this is the IPv6 routing header 0. This has been deprecated. This has been deprecated for the reason that one of the very well-known problems with source routing is that it can be spoofed to create things like routing loops, routing flaps, and so on. So essentially the idea behind source routing is that instead of letting IP figure out the best path by using routing protocols, the idea is I will tell you what path to use. Now, you may use routing protocols previously to let you know that, but in any case, it's not a dynamic path. It's a fixed path to say, I'm going to tell you, go to hop 1 and then hop 2 and hop 3 and so on, and each subsequent hop will take its own identification off. You can see how this can trivially be trivially be used to create routing loops. In fact, here is a packet of one where I have done so. So I just crafted that packet and created a routing loop. This becomes then another interesting question, is there are some extension headers that are potentially quite useful. Should certain extension headers be encrypted? Should they be authenticated? Should they be limited to certain domains? Again, another whole controversy at the IETF is this whole idea of things that are done in a limited domain, that is one administrative control. For example, in my corporate network, that is my network, I can do whatever I want because I control it. And so if I want to send unencrypted source routing packets, I shall do so. Because if in my internal network I have someone who can modify packets, then I probably have a much bigger problem than somebody creating routing loops. Although, depending on the nature of the routing loop, maybe not. So anyway, the routing header 0 was deprecated. Again, I think a deeper discussion needs to be had of whether we can use something like this with authentication or encryption or whatever. But to be honest with you, what I will tell you is I do not frankly believe we are ready to have that discussion probably for another 2 years. And as we get to the end of the presentation, you will see why I say this. So, some of the easy ones that you may already be familiar with from IPv4 are the ESP, Encapsulating Security Payload, and AH. Those are used in IPsec. IPsec, of course, was developed for IPv6, and then as you can see here, considering their IPv4 addresses, it was backported to IPv4, and it works exactly the same way. It works. The ESP and AH work the same way in V6 and V4. It was I believe there is some stuff about NAT traversal, but that's and there is no NAT traversal in IPv6. But other than that, the packet, the header itself works exactly the same way. And so here it is. Here is the AH header, which is the authentication header. That, as I say, it may be an interesting thing to wonder about whether if we want certain things to be authenticated, maybe we define an AH before the source routing header, something like that. Having said that, in implementation, in practice, what I hear from people is that IPsec is a pain in the neck to configure. Having said that, then it's quite well defined by now. So it is something we might want to consider is whether AH should be used in conjunction with other headers. And having said that again, I recall certain conversations at the IETF where people are considering deprecating AH. I will tell you, it is, sometimes I feel like it's like the little boy trying to stick their finger in the leak in the dike. Remember the little Dutch boy? There's so much going on at so many levels. It's hard to keep track of all these things. So anyway, you will notice here that OSPF is doing exactly what I had discussed, which is putting in an AH header before the OSPF header. And frankly, I think that makes all kinds of sense to do something like that. While you're in the process of setting up OSPF, go ahead and do that anyway. I'm not going to spend a huge amount of time on the AH header. As I say, we will be doing a series starting next year, talking about cryptographic functions and what they are, and security functions. So we will discuss things like hash algorithms, what they really are, HMAC, and so on, replay protection, what does MD5 really do, and why is SHA deprecated, all those kinds of things. And so what I will say, though, basically the idea behind authentication is that you're validating that the person who sent it is the right person to have sent it. You're not keeping it secret. You're saying that I'm authenticating that I have the right to send this. You're not doing integrity. You're not saying that I value, that I'm saying that everything is completely correct. Although the input to this particular hash algorithm is the payload of the packet. So there is some, with AH you have some level of protection, but it's not necessarily a checksum. ESP will actually encrypt the packet. That is certainly a way to go ahead and encrypt what you need. The problem, if you will, with ESP is that when you encrypt everything in the packet, anything along the path can't see what you have done. And of course, the people who are proponents of ESP will say that is the point, that nobody along the path can see what's done. But the reality of network diagnostics and network management is that many middle boxes serve a very useful function. You might think of firewall, for example. There is a reason we put a firewall in front of devices. People don't generally spend money to buy devices they don't need. Sometimes, of course, they're a good salesperson, but in any case, so if they need to see the packet and you're making it impossible, you're cutting off those functions. And this again is some of the objections that I have heard as to why ESP is not more widely adopted. So, what is the issue with extension headers? Well, so routers or other devices anywhere along the path, or other quote unquote, let's leave it very vague, other things along the path. And we'll talk a little bit more about why do I say it, make it quite that broad. Something along the path may drop the packet if they see an extension header in there. And considering that nice little source routing header that I was able to craft relatively trivially, you can see why. Now, just because something is deprecated by the IETF does not mean that you can't craft a packet using that. I mean, the IETF, as they say themselves, is not the protocol police. They can't police everyone across the world. And just because it's deprecated doesn't mean I can't craft a packet using it. And if if the software or hardware on your network device or your network interface has not implemented it, it will just flat out go in. So there are valid reasons for dropping these packets, and there are invalid reasons. And the invalid reasons are that, in my mind, is that I don't know what this is, and so I'm going to drop it. And that is a blind dropping of extension headers, which we may be seeing some of. That is part of the effort that we are looking into, is what is the real situation? Are extension headers being dropped? Really? And if so, why? And more on that in a moment. Another large issue is that the extension header may be too big. I believe by too big, they mean over 255 bytes. And so that makes it harder for the huge switches, the ASICs essentially, on the internet to read these packets. And so so then the processing is much slower. Now, this in some ways, frankly, does make sense. It is a large thing to ask that ASIC sizes should grow. Although, hardware is still continuing to improve. And to me, it does seem like you're getting a bit greedy. If you need that much metadata, I don't know. Just as a protocol designer, possibly you need a second packet or something different. There's something wrong with your design if you need that much. Again, that's speaking in the abstract. Okay, I'd like to see a real case where that was validly needed. Sure, privacy violations. Yes, indeed. You can read metadata. You can deduce a great deal from what is going on in the extension headers. And in fact, that is why for our own extension header, the performance and diagnostic metrics extension headers, we have designed PDM version 2, which is encrypted, because a great deal of not just privacy, but a great many other things can be violated by our extension header. So again, this gets back to, indeed, you have to think about privacy violations, and should it be encrypted? Should it be authenticated? What? Another large controversy is, can devices in the middle of the path, can a router, for example, modify the extension header? And if so, how? Certainly, if you add something to the extension header, you're going to likely have problems. It's going to throw your checksums off. Your AH probably won't calculate correctly. Heaven only knows what happens to the path MTU. You might force fragmentation or packet drops. So what do we really mean by change the extension header, not at the source? This is an ongoing controversy at the IETF, and as I say, this is not one that I feel terribly strongly on. If others do, please feel free to say, to speak up. It is in the nature, as some things evolve into a sort of a religious argument at the IETF, where there are some very large proponents one way and others who feel quite passionately the other way. Another issue, which I find to be actually quite valid, is doing a TLV kind of parsing, as we had talked about before. I think the original design was flawed. I think we should have always had fixed length headers or an index or some such thing. But again, I don't quite know if that ship has sailed, to use another IETF lingo that some people like to throw out when they do not wish a particular change to be done. Again, I think that is not, in my opinion, the largest issue at hand right now. I think there are a number of others. So, pros, as I have said before, is you can make it truly evolve. It becomes an extensible protocol, and hence the protocol has a very long maturity period before we really do need IPv6. So, and of course, this is self-serving. Is that, and of course, it's like, people, if you don't believe in your own work, maybe you ought not to be doing it. So I really believe that we really need something like embedded performance and diagnostic metrics in each packet. Again, I feel like it was a major flaw in protocol since day one, and I believe we are adding it back where it belongs. And we are getting some validation for this. As you will see, it has been accepted into the IAB workshop on how to monitor encrypted traffic. We'll talk about that in a moment. So there are many good reasons for this. Again, the unfortunate things is that you can do many types of malformed packets, and we need to be aware of that. You can do a incorrect or partial header. You can violate the header order, the option restrictions, and again, I have trivially done that. The other thing that you can do is, if you have something where you have an unknown option or something like that, where you have something which, if I get a packet, I send an ICMP message back to you telling you there's something wrong with that packet, then I can, again, trivially create a reflector attack. So if you do something like this, where you say destination option and then it's unknown, instead of dropping it silently, that's a problem too. So there are some reasons for doing this. And here's my nice little crafted packets with multiple and deprecated headers out of order, routing to the unknown or duplicate address, and so forth. So let us now get to the testing that we have been doing. And again, I encourage the folks involved in our testing to pipe up and put their 2 cents worth in at this point or any other point. So there has been a wide controversy at the IETF on, can extension headers really be used on the internet? And many people let me not say many people, a number of people have done some studies indicating that extension headers do not pass on the internet. Well, doing the studies that they did using the methodology they used to the endpoints they went to, that is a true statement. Whether that is an accurate reflection of that internet, the IPv6 extension headers don't work, is a different question. And again, to be reductive, there were essentially fake extension headers sent to things like the Alexa top-end site. And the reason we started working on this is, if all of this is true, if extension headers really don't work, and then no matter what I say about, this is just like the most useful thing, fixes all kind of problems, well, it doesn't work. And so why are you wasting your time on it, right? And so we're like, and so we said, well, let's not do that. Let's figure out what the situation is. And I will say it's because in my informal testing, I had seen it work. And so I said, well, wait a minute. There's something wrong with my lived experience and what people are saying. So let us find out where is the disconnect. And so here's a brief explanation of PDM. You guys can go up to RFC 8250 if you're interested. So what we did is, one of the things with not having a huge amount of money, which is really good, is that we just said, well, let's just use a small no-name hosting service that doesn't cost very much. So we just got some machines. I think it was like $6 a month for some FreeBSD machines, and we did a modification to the kernel to send our PDM extension header with every packet. And what that will do is, with real data that you send, that is, if you do an HTTP request, if you do an FTP, if you do an ICMP, whatever, then it will send it with every packet. It will append that, and that's done at the kernel level. So you don't have to do anything before that. And that the really important thing about this, in my opinion, is that it is true application data. It's not a crafted packet. It is real data from a real application for a real function. And so we did that. And what we did is we used locations throughout the world. We put them we intentionally chose a number of different continents. So Warsaw, we got Europe there, Toronto, North America, Seattle, North America again, Mumbai. So again, you can see we chose a bunch of different things. And the point was, if traffic goes from one to the other, it's passing the core of the internet. It is not going, just from my house to somewhere in San Jose or something like that. No, it's crossing the core of the internet, going all the way to the other side of the world. And let me thank a number of the people who were very key and instrumental in paying and doing work on the FreeBSD kernel and helping. Thank you guys so much. So, for example, here's a very large FTP that I did. It went from Toronto to Mumbai, crossing a couple of different continents. And you can see files transferred, and there was a bunch of different. It was a huge file, okay, a big old file. And interestingly enough, what you can see is you can see our PDM, but you can also see Fragment being transferred. It happens to be a jumbo interface at the source. So both of these extension headers are coming through. And here they are. Here's our nice little performance and diagnostic metrics header, and here is the Fragment header. Bottom line, and it worked everywhere. Work. And this is actually, we presented this at the IEPG, and we invited people to come to the hackathon and hack demo to see for yourself. If any of you also would like to see these traces, they are available. You can see them. And in fact, interestingly enough, we have been working with a number of other people doing pinpoint testing in various locations to test, and they are having success also. And I will tell you in a moment where we are not having success, but in a moment. So the other reason we really want to make this work is that more and more traffic is being encrypted. And our proposal to use PDM version 2, the encrypted version for monitoring encrypted traffic, was accepted by the IAB as one of the potential proposals. And so this will ideally get more traction and be more officially blessed. So what we are doing now is seeing where things don't work. Because let me state that the testing that was done previously was not wrong. It was accurate. There are times when extension headers don't work, but what is the reason that they don't work? And we have already found a major flaw in somebody who is doing, with part of the core internet infrastructure, they are working very closely with us. And to protect their privacy, I will not state further what the flaw is, but they are fixing it. It is, and they're actually looking at all their code in this arena, and working very closely with us to find other flaws, of which we are discovering quite a few. And if you would like to, we will be presenting these things at the IEPG, which is coming up for IETF 115. We also will have a number of drafts which go through and tell you, if you want to do such testing yourself, how do you do it for your own network, the kind of tests that we're doing? How do you test if your CDN is doing extension headers or supporting IPv6 properly? Same for cloud providers, routers, ISPs, and so on. And we want to test all extension headers, because if only in these 2 or 3 months we are finding major flaws in certain internet infrastructure, heaven only knows what we will find as we go forth. And as I say, we want to be very, very careful and do things very systematically, and then go ahead and write up what we have found, protecting everyone's identity, of course, and then give you the way that you can do this yourself also. I believe that we can find these problems and we can make extension headers work, but it will take some time to have this. So, yes. So, any questions from anyone, or Michael, Mohit, anyone else want to throw anything in?
Mike would like to make a comment. May I? Can you hear me?
Yes, we can hear you fine.
All right, first off, I cannot believe that you just covered all this information and all these topics in less than an hour. So hats off to you for doing that. All I wanted to say really though is, from an enterprise guy point of view, why the heck should we care about any of this? And my take on that is that our networks are not getting any simpler. In fact, just the opposite. They're getting harder to manage. And the reason we should care is that EHs will provide a whole bunch of great information and function and capability, blah, 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 to help us manage our networks of the future. We're going to need this. And the fact that it's extensible, there may even be more than Nalini has presented today in the future that will help us. And I'm going to throw out unabashedly that PDM is a good example. And Nalini, thank you for using that. I think that drives home the point that we can get free performance and diagnostic information. And it's accurate because it's part of the flow. It's not some external device telling us this and hoping that it's right. So it's stuff like that that will help us manage our networks. But to get this information, we need the EHs, the extension headers, to work consistently and perform well and be secure. And accomplishing that will not be easy, and it's already proven to be tough. So with that, I'm just going to say thanks to Nalini for all this information and for pointing out several potential issues and even resolutions to this. So thank you, Nalini, for blazing this trail. I know you've put a lot into this. This isn't easy. You're working with a lot of people to hopefully make our networks perform better and operate more disruptively or less disruptively in the future than we are today. So thank you for all of this. Appreciate it.
No, thanks, Mike. Now, I will say Mike has been, we've been together on this for the last, 12 years, and probably for the future 12 years. And so yeah, thank you to you for all your help and support. And I will say a couple of things. I'm getting some notes from people who are saying, how can they help in the measurement process and maybe work together? Please go ahead and contact me offline, and we can certainly, as I say, we want to control this very, very closely. but we can certainly we can put you to work if you want to work. And so thank you.
Let me encourage all of you enterprise people that, I mean, we're going to be a little intimidated by this, and for people that are as smart as Nalini, but this is actually kind of fun and interesting stuff, and I guarantee you will learn a lot. So please consider to help and participate.
Oh yeah, and as I say, we've farmed out tasks to quite a few people. Dr. Taliani, who is also on the call, he has quite a few students who are helping to work. One of the professors from a U.S. university is going to be helping us. And he actually made the point, he was kind of teasing me in a comment that he sent privately, that actually that the next version of IP would really be V10, as 7 through 9 are deprecated. True. But there's an IETF joke about V10, because there's a particular person who's been promoting this, frankly, not particularly well thought out proposal for V10. So V10 is kind of like, really V10? But the point being that there is no effort. There is no serious effort of any kind whatsoever to do anything but IPv6. So again, I encourage you guys to help. We can put you to work. We've got quite a few tasks. And there is one question about, how does the source device come to know it needs to fragment IPv6? That's a very, very interesting question. And I encourage you to read PathMTU, about PathMTU discovery. And I'm not going to, as I say, I'm not going to go into it terribly at this point, because there's a lot of efforts to change how PathMTU discovery is done. Yes. And whether everything really supports PathMTU discovery, how should PathMTU discovery be done? It's an easy question to ask, but it's not a terribly easy question to answer. How does the source device come to know? So, okay. So any questions, please let me know. We will make the recording available after the fact and send the foils out as always. And if you want to work with us, please do contact me. Thank you so much. And the next presentation in 2 weeks will be Amazon Web Services people talking about how the IPv6 implementation is on their platform, which should be very, very interesting. So thanks again, and we'll talk next time, I hope.